This is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to discuss the math buffer features which are a part of the frequency response measurement module. The frequency response module allows you to take frequency response measurements from a linear system to measure a variety of things, usually a microphone or a speaker response, but you can measure anything within the sound card's capabilities. The details on the module have already been covered in another video, but in this video I'm going to focus on the math buffers which are available in the Advanced Options button, which is available in the Plotting tabs section. When you click on the Advanced Options button, this dialog box will appear. It has options such as being able to adjust the line weight in the plots, but the main feature of it is taken up with the math buffers. To get a better view on this dialog box, I'm going to go ahead and open up Aries. I have a file already prepared where a number of measurements have already been made. I'm going to go ahead to the first example we're going to cover, which is currently selected. I'm going to go to the plotting section and then click on Advanced Options. So here's the dialog box. The actual math buffers will be shown in this section down here. Presently, you can see 5 math buffers at any one time, but these are all currently disabled. To create a new math buffer, you'll click on Add New Buffer, and the first set of controls will become available. If you create more than the 5 that can be shown at one time, this scroll bar over here will be able to allow you to scroll through all of your math buffers. You will tell Aries what type of buffer that you're going to enter. We'll show this in a little more detail in the examples. You'll assign a name for that math buffer. This is what will appear in the legend of the plots, and then the mathematical expression that's used. To refer to data in one of the data sets, each data set is listed here with a letter put in front of it. The letter denotes the data set that you're going to access the data with, and then the different fields within that data set are shown in this list here. So LR is the transfer function from the left input channel over the right input channel. LO is the left input channel over the the left input channel over the output channel spectrum. And then this is the transfer function for the right input channel over the output channel spectrum. L and R would be the spectrum for the left and right channels, input channels respectively, and then O would be the output channel spectrum. So for an example, I'm going to type in A for the first data set, dot L, meaning the left channel spectrum. I know that the left channel was measured from the microphone, so that's going to have units of pascals. And I'm just going to multiply it by 10 just for a simple operation. I'm going to go to the name field and I'm going to call it A times 10. And for the units type, I want this to appear in the magnitude plot, and it's going to have units of pascals because I know the left channel is pascals. Then I'll select plot, I'll hit OK, and here we see the math buffer automatically plotted along with the magnitude response of the first buffer. And the difference between the first data set here in blue and our math buffer result in green is 20 dB or a factor of 10. So that's a simple way of doing a quick math buffer operation. To turn the math buffer lines on and off, you have to go back to the advanced options and select or deselect whether you're plotting. Note that the graph is updated right away. If you click on that, it changes underneath it, so you can drag your dialog box off to the side and see the results immediately that you're typing in here. If you're typing in an equation to get it to register, you need to press the Apply to Math Buffers Graphs button here. So I'm going to exit from here. To demonstrate how this works, I'm going to go through a series of 3 examples, not including the one we just did. The first one is to look at changes to a measurement environment. One of the more common features of the math buffers is just to normalize one frequency curve by another frequency curve. In this case, we're going to measure the pressure response from a speaker 8 inches above using this electret microphone. This is a May measurement speaker, and that's connected to a May 206 amplifier, which will supply power to the microphone. And we're just going to measure the response at 8 inches away. Then I'm going to change the environment a little bit and remeasure those responses. So I'm going to do 3 modifications. One is to just put a relatively thick black cloth on top of the speaker and see how it affects the frequency response. Then I'm going to put a very thin, stiff cloth over top of the speaker, which has quite a bit more resistance than the black cloth. And we'll see another change. And then I just put a cardboard box on top of the amplifier to change the environment a little bit and allow us to see what that might do. Obviously, we're probably going to get a reflection off that box, which will travel up to the microphone and have some kind of an effect. And the purpose of this demo is to be able to clearly see the effects of these 3 different environment changes. So I'm going to go back to Aries, and this already is the data from that microphone at 8 inches away without any modifications. The second graph, the second data set, is actually an identical repeat of the first data set, just seeing how repeatable the measurement itself is. And you can tell these curves are pretty much on top of each other, but there is a little bit of difference. If we zoom in down here, you can tell that the green and blue curves are not perfectly identical, but it's hard to see how much variability we actually have with this type of a plot. So we're going to create a new math buffer plot, which will show the difference between these. I'm going to go back to advanced options, and this time I'm going to type difference between A and B, and for the argument I'm going to use the B data set, the spectrum for the left input channel, and I'm going to divide it by the spectrum for the first data set and the left input channel again. And I'm going to select plot. But if I leave this as Pascal magnitude, it's going to put that data into the frequency response measurement, and it's going to normalize the level up to 94 dB, which is not really what we want. So I'm going to have this go into an independent graph. I'm going to select for the type a custom magnitude graph, which will cause Aries to create a whole new graph just for the magnitude responses from the plot buffers, from the math buffers. So here we can see this is plotted in dB because this is selected. So the transfer functions are pretty much identical, so their value is around 1, a linear value of 1, which is around 0 dB. Our repeatability is within about a half a dB across this spectrum, and a little bit more where we have a minimum in the response. Now the actual data has a lot of detail and colorization because this response was measured in a normal room, not in an anechoic chamber. So there's lots of reflections off the walls and off the table and whatnot. Had we done this in a more controlled environment, this would be a lot smoother. But we still see a general trend if you kind of draw a line through those dips and valleys. And here's the difference. So if we just repeat the measurement, we can get within about a half a dB pretty consistently. So I'm going to hit OK. And now I'm going to plot the curve when we add the thick black cloth. So that's shown in red. So that is a little bit less than the other 2 plots, particularly in this range. Not sure exactly what's going on here. It's hard to see it. So let's go ahead and plot the difference. So I'm going to go back to advanced options. I'm going to create a new math buffer. I'm going to go ahead and put it in the magnitude response. I'm going to call this diff A and C, and its math expression is going to be the C dataset dot L divided by the A dataset dot L. I'll go ahead and plot it, and I'll pull this over. So here we see the difference between the black cloth and no black cloth. So the black cloth is causing some attenuation between about 3 and 5 kilohertz. It's actually increasing the sound a little bit around 2 kilohertz and causing, again, a bit of an attenuation at the higher frequencies. So it's nice to be able to amplify and see these differences a lot clearer. Now, if we want to go ahead and do the other data sets, it's kind of obnoxious to create a new math buffer expression for every single data set, particularly if you're adding new frequency responses time after time after time. If you've got 30 frequency responses, you don't really want to create 30 math buffers. So there's a concept in these math buffers where you can create a generic math buffer by not referring to a data set. So I'm going to come up here and I'm going to delete the B period and just have an L here. So Aries will look at this and say, oh, L, it's just a generic left channel spectrum. So what it will do is it will use the data from all of the data sets selected for plotting, and it will one by one evaluate this math buffer and use the left channel spectrum of each of these selected data sets to create a new graph. So this is just operates on generic data if you don't specify the data set name. So with this is just going to be the difference with A of whatever data sets that's being plotted. So I'm going to go ahead and delete the second data set because that's going to be redundant. I'm going to hit OK here, and we're going to come back. And now we see the math buffer difference with A being evaluated for the A buffer, which is going to be perfectly 0. There's a blue line there that's perfectly 0, so it's normalizing the A buffer with the A. I'm sorry, normalizing the A data set with the A data set is identically 0 dB. Here's the previous normalization we did with the second data set, the mic at 8 inches repeated, and then with the black cloth as in red. We can go ahead now and just click on with the white cloth, and that shows the response, the difference in the response with the white cloth. Then finally click on the graph for the box when the box was put in place. I'm going to turn this graph off to give us a little more room up here. And we can see the details a little better. Now this is plotting the A data set being normalized to 0. That's kind of pointless. So I'm going to click on this and turn this off. So now the math buffer is only being evaluated for these 4 data sets, and we can see the difference in them. The white cloth made the most amount of difference. The black cloth attenuated the high and low frequency a little bit. Didn't do too much around this minimum here for some reason. And then the box shown in this cyan color, it's adding to the response, subtracting the response, adding, subtracting, adding, subtracting, adding, subtracting. This is a classic example of constructive interference and destructive interference, constructive, destructive, etc. So you can kind of get an idea of what the box is doing there. Obviously, the mean free path between the direct path and the reflected path is causing the periodicity in this response. So that was a quick example of how you can use the math buffers to accentuate differences in plots. Now we used a number of operators here, but they were pretty tame. I think we just used the divide operator. You obviously have all the standard math operators, plus, minus, multiply. There's a power operator. There's some logical operators which might have some use for you. If I go back to Aries and I'm going to go to advanced options, I'm going to not plot this math buffer. I'm going to create a new math buffer, new math buffer. And I'm interested in, let's say, what are the frequencies greater than 90 dB? So I'm going to type in an equation where we have dB. It's going to convert this to decibels using 10 log base 10 expression. And I'm going to do the L spectrum. I'm going to divide this by 20 micropascals, 20 e to the negative 6. And I'm interested in when this is greater than 90. And the name of the buffer will be greater than 90, question mark. I'm going to put this in the custom magnitude graph and select it for plotting and hit OK. And nothing got plotted. Let's go back to advanced options and see what went wrong. Okay, so I got e to the negative 60 instead of e to the negative 6. So I'm going to go ahead and hit OK again. And now we've got something here. So dB is off. For the frequencies where the SPL is greater than 90, we have a value of 1, a logical value of 1. If we have the frequencies, its logical value of 0. If I turn dB on, we can see that these are the frequencies where the spectrum is over 90. So perhaps you could use this as a mask test or something like that. So that might be some use for these logical operators. There's also some built-in variables that you can use. F is for frequency. W is the radian frequency. J omega would be the complex frequency. So this is basically square root of -1 times omega, which is useful sometimes. J and I are also both variables that can be used. And you can just type in pi to represent pi instead of typing in 3.14, whatever you want to use. And then you have these functions here. This is the dB function that I use to compute SPL. If there are any other operators or functions that you're interested in, please contact us and we'll be happy to add them to make this feature more useful. The next example I'm going to show you is to use a series resistor to measure the electrical impedance into a speaker. Here I'm going to put a 10 ohm resistor in series with a speaker, and I'm going to measure the transfer function of the electrical signal over the resistor and the speaker divided by the signal at just the speaker itself. So I'm going to use the left over right transfer function to measure the transfer function between these 2 points. If you do that, I've got the math here, which is showing how that transfer function from the left and right channel can be used to compute the electrical impedance into the speaker. I won't go through this math, but the result is you take your series resistor R, which is 10 ohms in this case, and you divide it by the transfer function from the left and right channel minus 1. So if you compute this quantity, the result will be the electrical impedance in ohms. So I'm going to go ahead and do that. Return to Aries, and I've got another module instance with the speaker impedance data. So the first data set listed here is the transfer function from the speaker and resistor voltage divided by just the speaker voltage. I'll turn the real and imaginary parts on. I'm going to go to advanced options and increase the thickness of these lines here. I'll change it to 2 to make it a little easier to read. So here's the magnitude of that transfer function. Here's the real and imaginary part of that transfer function. Already you can see something's going on here. Kind of looks like an impedance for a speaker, but not really. We need to do our math transform on this first. So I'm going to go to advanced options. I'm going to create a new math buffer again. I'll go ahead and select this for plotting. There's nothing typed in yet, so that's reporting an error. I'm going to put this into a custom graph that shows the real and imaginary components. I'm going to call this Z-speak, and the expression is 10 ohms divided by the A dataset dot LR, so that's the left over right transfer function, minus 1. So that's our expression for impedance. If I select plot here, it creates that plot, and shown down here is our electrical impedance. So I'm going to hit OK in that dialog box, and I'm going to stop plotting the transfer function data and just plot the impedance. So this is about an 8 ohm driver. There's a resonance just under 600 hertz. There's some more detail up around 3 kilohertz or so. This might be the breakup mode of the cone, higher order breakup mode of the cone. Then at the higher frequencies, they settle down, and the resistance is pretty much purely real around 8 ohms, and you do get the inductive term at the high frequencies. So from that and a resistor, we've measured the electrical impedance into the speaker, which was pretty handy. Now, some sound cards have some kind of a non-ideal transfer function due to the amplifiers for the sound card or due to a latency from the left and right channel with the sound card. So we may need to take that into account. An easy way of doing that is to measure what I'll call a calibration transfer function, HCal here, which is the left and right signals divided by each other when they have an identical signal on both channels. If the sound card is perfect, this is just a simple value of 1, unity. But if there's any magnitude or phase differences between the channels, this will capture it. We can then normalize out our speaker transfer function by just dividing hspeak by hcal and then subtracting 1 from that. So I'm going to go back to Aries, and I did that measurement. That's shown here. I'm going to go ahead and plot the real and imaginary portion of that. And you can tell that that transfer function is pretty much unity, and the imaginary part is pretty much 0. So there's little magnitude and phase variation to it. But I'm going to go ahead and use this and see how much it corrects our transfer our electrical impedance measurement. So I'm going to return to advanced options, create a new math buffer. I'll call it ZSpeak with correction. And the expression is now going to be 10 divided by A dot LR, our measurement, divided by our calibration, B dot LR minus 1. So that's our new improved impedance measurement expression. I'm going to make this, put this in the custom real and imaginary graph, select it for plotting, and if I hit OK, I'm going to turn that first plot off. So the blue curve was our original curve, and our green curve is corrected with that calibration transfer function. The imaginary part is pretty much identical, very little change, but the real part, let me zoom in here, it increased the real part of the resistance from about 7.95 to about 8.05, or about 1/10 of a dB. So the difference between these two plots are about 1/10 of a dB. I guess we could plot that difference with the math buffer, but I'm not going to bother with that. So that was a nice example of how these math buffers can be used to measure the electrical impedance into a speaker. The final example I have for you is shown here. I'm again going to measure the pressure response above that same speaker. This time it's at 12 inches away. And I'm interested in what the particle velocity is at the mouth of that speaker. If you're familiar with loud, high-intensity speaker systems, you know that you can get some nonlinear jetting effect out of small ports and bass reflex ports and whatnot. So I might be interested to know what's the particle velocity exiting this speaker. If it's much greater than 1 meter per second, I might be concerned about some nonlinear jetting effects. So I'm curious to know what the particle velocity is there. We're just going to approximate this by assuming this is a simple baffled source. This is the spherical wave propagation formula for a simple baffled source. Q is the source term that has units of cubic meters per second. K is the wave number. Rho is the density. C is the speed of sound. R is the distance, the radial distance to your measurement point. So Q, the source strength, is going to be the particle velocity times the surface area of this throat on the speaker. If we just look at the magnitude terms and get rid of the complex terms, the phase delay part of that exponential, just look at magnitudes, and we substitute omega over c for the wave number k, we end up with this expression. So the pressure is equal to the particle velocity times the surface area divided by 2 pi r, and then that's multiplied by the radiant frequency and the density. Solving for the particle velocity v, we have this expression. Now, if we want to type that in as a math buffer, we'll use something like this. We have the magnitude of the pressure. We'll enter that in as the left channel for our data set. 2 times pi. The radius is 12 inches or about 30 centimeters or 0.3 meters. I'm just going to type that in as is. We've got a variable for omega. We're going to use that. I'm going to use 1.2 for the density, just a rough approximation. You'll be able to just type in pi. And then for the surface area, of course, is pi r squared. So here we've got another pi, and we need r squared. The diameter of that is 1 inch, or 25.4 millimeters. We want this in meters, though. So we take 25.4 millimeters divided by 1,000 to get meters, divide our diameter by 2 to get radius, square it, and so now we've got radius squared in here. So I'm going to go ahead and type this in to a math buffer for us. So I've got to go to a different module. Here I've got one where I measured the response at 12 inches. The left channel is the response at 12 inches. Here's what the pressure response looks like. Again, we have a lot of colorization due to reflections in the room against the wall and whatnot, but we're just looking for an idea of what the velocity is out of that speaker. It's hard to predict what it is just from this pressure response. So I'm going to create a math buffer in the advanced options dialog box, create new buffer. My name will be V meters per second, and my expression, if I can remember what I'm supposed to type in here, I'll use A.L. I want the left channel spectrum for the A buffer. I can type in ABS here, but it's already a magnitude spectrum. I'll put it in there just for completeness sakes. And I don't remember what I want to type in now. Numerator is 2 pi 0.03. So I'm going to type in times 2 times pi times 0.3. I'm going to divide it by the numerator. I'm going to have some details here. I know I could just cancel that pi, but I'm going to leave it in there just for completeness sakes. Go back to the slide. So we got omega times density times the surface area. All right, so we got omega times W for omega times 1.2 for the density. Now we need the surface area times pi times, and we want the radius squared. I know the diameter is 25.4 millimeters. Divide that by 1,000 to get meters. Divide that by 2 to get a radius. And then I'm going to use the power operator and square it. And that should be our function. So I'm going to put this into a custom magnitude graph. And I'm going to select this for plotting and hit OK. And here's our velocity graph. Now this is in dB because we've selected dB over here. We've got to turn this off if we want linear units. So here's our linear units in meters per second. For the most part, the velocity is under about 0.1 meter per second, so there's certainly no chance of acoustical jetting. We do have a resonance that's producing about 0.3 of a meter per second, but that's probably still okay. If we saw numbers come in up around 10 meters per second, we would probably be concerned about jetting out of our port and want to try to address that. So these have been 3 examples of how to use math buffers. Sometimes it can be hard to know how to use these tools, so I tried to give you 3 fairly different examples of how to use them. If you have any questions about how to do some operation that you're interested in, please contact us. We'll be happy to give you a hand. If you have a question about how to apply math buffers to your problem, please reach out and contact us. we'll be happy to help. And thank you for your time. Hope you found this useful.